Yeah. Okay. So let's continue with the tutorial. Oh, yeah. Okay. Okay. All done. Okay. So I will show you how to use the previous technique in the acyclic case. I mean, it's a simple extension. I'm not going to show you all the details. What I really want to show you is in the second part of the first part of the tutorial, not the second part of the tutorial. So I have way too many slides. What I want to show you is the other technique that is widely used in the area, which is this idea of using this Horwitz-Thompson estimator. So, I mean, and with that, actually, I think I will be happy, actually, if I manage to show you all that. Okay, so how do we do sampling in the acyclic case? So consider, in this case, this acyclic query. You fix a joint tree, right? So assume that we have something like that. And let's use this relation here indicates that R sub I is a descendant of R sub j in this joint tree, right? Okay, so then, as in the previous case, if we can do exact counting, we're interested in this quantities W of t, which is the tuple t join with the joint of all the children, right? That's what we are doing here, right? We take all R sub j such that, not only children, all the descendants, actually, sorry. You take all the R sub j such that R sub j is a descendant of R sub I, and then you do the join, right? Exactly like in the previous case, but now we're considering a tree, right? And we also have this quantity here, right? Which is if R sub j is a child of R sub I, we like to say, well, here what we are doing is we are essentially counting all the tuples that we have from R sub j, right? But considering this is restricted to t, right? So we're doing R sub j, all the descendant of R sub j, and we are doing the join with this t, right? What is important here is that, as in the previous case, we are not going to have this w. We are going to replace this by uppercase w, which is going to be an estimation, right? And you want to have some properties which are natural properties, and as before, we expect this w to be larger than or equal than to the previous value. We expect this also to be true when you consider these predicates where you're considering children. So you're saying if t belongs to R sub I and R sub j is a child of R sub I, then you should have this relationship here. You expect W t be equal to 1 when you have a leaf. Again, the same process when you were thinking about the last relation in the join. And these are very natural conditions. Actually, you will get equalities if you are thinking about this lowercase w. But in this case, you are expecting that if you take wt and you consider the numbers that you are going to get for the children, right? Since when they are doing the join, actually, what you have to do is to compute the multiplication, right? You don't have variables in common between these R sub k1 and R sub k2, which are not in the parent, right? You just have to combine these tuples by doing essentially if you're thinking about counting the multiplication, then you expect this value wt to be larger than the values that we have here. And also we have this final condition that is the same that we had before, right? You expect this w of t R sub j be greater than this w when you evaluate it in the semi-join. And this w for relation is just defined as before as the sum of the w over all the tuples. So it's a set of actions like the generalization to what we had before. And then the procedure is as follows. Actually, it's not that different from before. You will sample with some probability and reject with some probability, and you will do this in every element of the tree, right? So you sample with the probability that we had before, we reject with some probability, and now notice that this probability that also depends on the estimation that we have for the children, right? Here we have R2 and here we have R3, right? So it depends on this estimation that we have here. We know this quantity, it's actually a probability because we know that this is smaller or equal than this value here, right? And as expected, actually this should be R2 and this should be R3. There is a typo here, right? So because here you are sampling considering, okay, I already sampled this tuple R1, I consider the semi-join, how big is that? And I compare with the size of the whole set, right? And I reject with probability, again, as before, proportional to this W of R2 divided by this W of this quantity here. The quantities are not really important. The important thing is that when you put all together, you simplify things and you obtain what you expect, right? And the same thing here, this is R3, and we do this thing here. So actually, when you multiply this thing, okay, so sorry. So when you want to compute the probability that the tuple is in the answer, you have to consider that you have to accept, not to reject, right? So the probability of accepting are this one here. And when you multiply all these things, you say, what is the probability of R1, R2, R3 is generated? It's just a multiplication of all these probabilities here. And you immediately will see that you start simplifying terms, like this one is here, this one is here, and at the end, what you get is this WR2, WR3 divided by WR1, and these two are leaves in this case, so this value has to be equal to 1, so what you obtain is 1 divided by WR1, right? Exactly what you had before. It's just that you need to consider a process where you are considering the childrens of a node. So it's not different from what we did before. Okay, just a few words about sampling in the cyclic case. This is not I would say, satisfactory solution, but it's a solution that could be used in practice. There are better methods. So here is, you have a join query, right? But that is cyclic. And the proposal here was to split Q into two queries, QA cyclic and QRest. Essentially, QA cyclic it's a query that is acyclic. QRest is a query that is going to be cyclic, right? And what you are going to do is you are going to use the algorithm for acyclic queries here. And here, what you are going to do is just to do, and you're going to use an exhaustive algorithm, right? You are going to do counting, actually, right? So you have to really solve this question. If you do that, you can do sampling. So assume that the A1, AK are the common attribute between these two queries, right? So then you need an estimation as before. I mean, let's call it this MRest. The only thing that we are saying here is, okay, let's consider all the possibilities for these common attributes. And in this query QRest, let's count the tuples where we have. So for every combination, we count how many tuples have these values, right? And then we compute the maximum, right? So this is giving you a bound on the number of tuples that you can do you can have in the join, right? Because here you are joining this QA cyclic with QRest. So you are saying, if I have a tuple here, with how many tuples can I join this there, right? This is going to be a bound for that quantity, right? So, and then you do the sampling exactly in the same way, right? You say, okay, in order to do the sample, use the sample algorithm for the acyclic case to generate a tuple in QA cyclic. This you can do it efficiently. Then reject with probability that is going to be proportional to this QRest semi-joined with T. So here you will have to compute the answer to this QRest. So what you expect is that even if the query is large, hopefully the part that is cyclic is going to be small, right? Hopefully you can divide this into a query that is large and another one that is small. And then you are going to generate uniform randomly a tuple from this QRest. Again, exhaustively, you don't have an algorithm to do that, right? Or an efficient algorithm. And notice that the tuples are generated uniformly, not efficiently, uniformly, because the probability that T prime is generated is the probability that T is generated times, again, the probability that T prime is generated given that T is generated, and you are going to be in a situation similar to the previous one, right? The probability that T is generated is 1 divided by this quantity, what we had before, the algorithm for the acyclic case. Then you have to accept, and the probability, sorry, this is the size, right? The size is missing here, is the size of this QRest semi-joint T. And here you have this MRest, which is a quantity that doesn't depend on the tuples, actually. So you simplify these two values here, and what you get is this, which is similar to the bounds that we have before, right? You're saying W of R1 times this quantity that we have here. Okay, so it's going to be uniform generation. But with the caveat that here you have to do some, or you have to compute the answer to QRest, right?
Since the split is not unique, yeah. Can you take? It's almost like generating another query plan, right? How do you choose?
Yeah, actually, I didn't know that, but one of the co-authors of that paper is here. And actually, they have some optimization techniques. Maybe you can say a bit more, actually, about, because one of the topics, actually, when you're trying to do this thing is how you choose, actually, these things. Yeah. I don't know if you want to say a bit more.
I think for the cyclic one, we are not doing a very good job, because, in the last pause, there are two papers studying how to do uniform sampling over the cyclic ones. And I think this one is just for maybe practical implementation. We want to transform a cyclic one into an acyclic by breaking some join conditions. yeah, I think there are many different choices how to do this transformation. I think it quite depends on the practical data set and the
So if you take the triangle, there are 3 ways to do it.
Yeah, exactly. Yeah.
Which do you choose? What's the right?
bound for cyclic.
Yeah.
So, I mean, in this case, I don't. Okay, in the paper about one join, actually, they have some techniques to choose the right order, actually. But it's different from here. It's not that they want to divide it into queries, actually. They want to sample in some order. I will show you, I mean, how it works, actually. But here, I don't know, actually. I don't know how you will do that. Okay. Okay, so let me tell you a bit about now estimation of cardinalities and aggregates. And now is when we are going to talk about this Horowitz-Thompson operator, which I think is if you want to learn something from this tutorial, this is one of the important things. Okay, so one thing is that here what we want to do actually when we are doing estimation of cardinalities and in particular of aggregates, when we say, okay, we want to compute the sum in this column and we want to have an estimation, we need to have, we need to construct an estimator, and we also need to think about confidence intervals, right? We would like to say, okay, we know that with certain probability, the answer is going to be inside this interval, right? And when you do that, you rely on estimators. I'm going to say just a few things, probably you know all these things that I'm going to say here. Remember that just when you have an estimator, we talk about the bias of estimator, which is the difference of the expected value of the estimator and the quantity that we want to estimate, right? This is a usual thing. And in general, we want unbiased estimator, right? We want this bias to be 0, right? We want to have an estimator such that the expected value of the estimator is the value that we're trying to estimate. The second property that is very important, is very useful in practice, is that the estimator is consistent, right? Which means that it converges in probability to this value of theta. Actually, if you don't know the definition, this means the following. In this estimator is going to depend on some n. This is usually the case, right? The number of samples that you make, right? And the larger this n, the better that the estimator should be. And this is what you are saying here. You're saying that for every epsilon greater than 0, if you think about the probability that this estimator, actually minus theta, is greater than this epsilon, you take this probability and then you take the limit when n goes to infinity. This limit has to be 0. Yeah.
Marcelo, the first bullet, theta seems to be a number.
Yeah, this one?
Yeah.
Yeah, here also it's a number. Yeah, it's a number. I mean, you are converting to this value actually, not to a distribution actually in this case.
I see. So
the
theta hat is actually a number.
No. Theta hat is an estimator, and theta is a value, right?
Okay, so then how can the theta hat is a random variable? How can that random variable convert to a number? You really wanted to concentrate around.
You are thinking about when you think in terms of distribution that has only one value, theta, right? I mean, maybe it's very interesting in this way, right? So this probability it's well defined, right? You are thinking about the probability, this is a concrete value, and you're thinking about the probability that this estimator that you have here minus theta is greater than epsilon, right?
And this is the definition of the arrow above, right?
In which sense?
Because the bullet explains what the previous one is.
You mean this? This one. Yeah, this one.
That was saying that what does it mean for a distribution to converge to a value?
This is okay. Sorry, you're talking about this one. Yeah, the definition of converging probability is this one here, right? Yeah. Okay, sorry. Yeah. Now that was a confusion. Okay. Yeah.
Marcelo, you have an example of a consistent biased estimator?
Yeah, I mean, something that you could do is like, for example, the average, right? The average is it's defined like this, right? And in general, it's going to be unbiased, right? But suppose that now you define the average prime, whatever, like this, for example. Yeah, this is from 1 to n, right? From 1 to n, right? So if you think about the expected value of this guy, right? It's going to be like n minus 1 theta, right? So this is biased, right? But it's going to be consistent, right? Okay, so this is something that you ask to the estimator, and in our particular case, not from the work of from statistics, we will also want this theta to be computable in polynomial time, and actually very efficiently in n, right? Okay, so just a few words about confidence intervals. So in general, what we want to provide is something like this, right? We would like to say that the probability that theta is in this interval here that depends on the value of the estimator, right? There are two functions, f and g, and I want this theta to be in f of this, depends on the estimator, right? And g, I would like this to be greater than 1 minus delta. I write it like this because usually you say delta is a small quantity, right? I want this probability to be large. But okay, in general, what you want to have is something like this, right? You want to have that the probability of theta is in this interval that is the value of your estimation minus plus some epsilon that depends on n. You want this value to be greater or equal than 1 minus delta, right? This is usually what you want. And a couple of comments about what are the fundamental tools to construct confidence intervals. Well, the first one is the central limit theorem that I assume that you all know. Something to consider there is that the confidence interval depends on the convergence rate, right? So, which means that you have an approximation, right, of the confidence intervals if you fix a value n, right? So this is something to consider. And there are some like interesting tools that you could use actually to not to have this problem, like this very Essen theorem actually, which actually gives you a precise bound of the different with the standard normal distribution under some assumptions for the variables that you are considering, which are assumptions that are usually satisfied, right? And this is one tool that you could use. You get like larger confidence intervals, but you know that actually that you are with the high probability that your estimation is going to be, so the value that you're trying to estimate is going to be in the confidence interval. The other set of tools that are usually used here are the concentration inequalities, right? Chebyshev, Hefdin, which are the bounds that are produced are not approximation. Don't depend on a conversion rate, but they are looser, right? Usually you produce like larger intervals, but these are usually very useful tools. And in both cases, both for the central limit theorem and for the concentration inequalities, what you want to use is estimators that have a small variance, right? This is very important actually, because usually the sizes of these confidence intervals depends on this variance. Let me just give you a simple example. Probably you all know this. The Chebyshev inequality, I mean, this is the usual way that you write this inequality, right? You think about the probability that the x minus the expected value of x is greater or equal than epsilon, and this is smaller than, sorry, this should be an x, right? The variance of x divided by epsilon squared, right? And if you put it in terms of an estimator, and you say that theta hat is an unbiased estimator of theta, then you can write this inequality just, so this Chebyshev inequality as follows. You are saying that the probability that theta is in between this theta hat minus epsilon and theta hat plus epsilon is greater or equal than 1 minus the variance of this theta hat divided by epsilon squared, right? So if you want this probability to be large, you need this value of the variance to be small, right? This is just a simple observation, but this is what you usually want in practice. You want estimators with a small variance. Yeah.
I'm not very happy with having that.
No.
So in the equation above, x is a random variable.
Yeah.
In the equation, and e of x is a number.
Yeah.
In the one below, theta hat is a random variable.
Yeah, but this is also random variable, right?
Yeah. So x is theta hat.
Yeah.
And this is what you want to estimate. So you really need to take the variance of theta hat, but this is.
Yeah. And this is theta hat, it's just a random variable. You can think of this estimate as a random variable, right? And here you have the expected value of this theta hat, right, which is theta, right?
And there should be variance of x.
Yeah. Sorry, I said, yeah. There's a typo there. It should be x, yeah.
You really have to estimate the expected value of a random variable. And the probability depends on its variance, not on the variance of your estimator. This is what bothers me.
Okay, so maybe there's something that I'm not seeing. Actually, what you want to say is, okay, what is the probability that the value that you estimated is in between your sounding?
I know exactly what bothers me.
Yeah.
What bothers me is in the second, if you want to make a second formula instead of the first one, it means that your theta is the expected value of theta hat.
Yeah, that's why I'm saying that I have an unbiased estimator.
I see.
Yeah, so the expected value of this is theta. Yeah.
But you're not estimating an unknown quantity. What you're really estimating your expected value. So
yeah, you're estimating this value actually, right? It's a value that you don't know. You know that this is just unbiased, so you know that the expected value is going to be this unknown, right? And what you are saying is that this unknown is going to be in this interval with this probability, right? Yeah.
Okay, so you want this assumption. Good.
So, Hannah, you had to.
I think you may want to swap the half and the theta in the second inequality.
Okay, but this is the usual way that you think about intervals, right? You are saying my unknown is in this interval, right? You
But
can.
the unknown is still a half, not theta.
No, your unknown is theta. Actually, that's what I'm trying to estimate.
I
Actually.
mean, your estimator is within 1 minus epsilon of the quantity you want.
Yeah, but I mean, why do you need an estimate if you know theta, right? Yeah, I mean, if theta is unknown. Theta is the value that you don't know, right?
Right.
Yeah. So this is what that's the reason why I like to think in this way, right? Because you are saying, what is the probability that this value is in this interval is greater or equal than this quantity, right?
It's equivalent, but I'm just saying
Yeah.
that intuitively that it's unknown, but whatever you're producing is within plus minus epsilon.
No, they're equivalent. Yeah, you can switch these two things. I like to think it in this way, actually, right? I mean, in the sense that in practice, what you like to
Marcelo,
Yeah.
for hefting, you don't need the variance, right?
For hefting, you don't need the.
This is Chebyshev.
Yeah, this is
but
Chebyshev.
because you mentioned before that Chebyshev and hefting, it is important to have small variance, but hefting doesn't use the variance, no?
Yeah, hefting doesn't use the variance. Yeah.
It's kind of implicit. Because
Yeah, it's kind of implicit, actually. Yeah.
Yes.
It's
So-
not used to be.
Exactly, yes.
Yeah.
But what Hank was saying, that you want the interval to be fixed. I want to say I want to be within 10% of the value. And the random variable should fit that interval.
Yeah.
But
Yeah.
in your case, your interval.
But they're equivalent, right? It's just a way that I like to think about this. It's like in practice, what I'm going to get is the value of this guy, right? And I want to say, okay, what is the probability that this guy is in this interval? I can produce theta hat, right? I mean, I do some sampling, I produce theta hat, and I want to say what is the probability that the unknown is in that interval. That's the way that I like to think about this. But you are right, actually. Another way to think about this, you switch this thing, and you say, what is the probability that theta hat is in this, in this interval around the unknown value. So I'm close to that value. Yeah. So clear? Yeah.
I think we're happy.
Yeah, you're happy. Okay. Okay. So let me show you now the this Horwitz-Thompson estimator, and I will do it in a very concrete work. And this is the work on Wander join, actually, by KG and collaborators, right? So the idea here is the following. Suppose that you want to do you want to answer the following query. You have a join, but now you want to compute the sum in over this attribute D that you have there, right? Okay, so how can you do this? You do the following. So suppose that these are the tuples in the relations, right? And here, actually, you could say, okay, we are going to do, let's construct a graph that, I mean, conceptually will show you what we are doing, actually. So you are going to put an edge here if they have the same value of if these two tuples can be joined, right? So what we are saying here is that R1 of B is equal to S2 of B, right? So these two guys can be joined, right? So and suppose that we have these possible joins in these relations, right? And notice that we need to have an structure like this because R2 can be joined with these two guys, so they have the same value, right? In the attribute B. So if this can be joined with this, it has to be, then it can be joined with this one. Okay, so now what we're going to do here is just a random walk, right? So we're saying, okay, we're going to select one tuple from R with uniform distribution. So we're going to have here this R1 with probability 1/3 or 1 divided by the size of R. And then we say, okay, we have two edges here, right? And we have to pick one, and we will do it as a random walk. So we're going to do it with, in this case, well, with probability 1/2, right? So and suppose that we pick this one here, and then we say, okay, now with probability 1/3, I have to pick one of the three values here. So I will pick this T4 here, right? So what I get is, okay, the probability of generating then this path here is equal to 1 divided by, or 1/18, right? Is because it's 1/3 times 1/2 and times 1/3, right? And this contribute to the answer to the query in a certain value, and this certain value is T4 of D, right? So for this tuple here, actually, okay, I'm denoting this as a tuple, right? But when you compute the join, in this row, you are going to have as the value in the attribute D, this T4 of D, right? Very simple. Okay, but there are other tuples that you can, or partial, or actually they're complete path, actually, but they don't represent tuples in the join, like R1 is 1. I don't have any value that could be I can use in the join. that are going to have some probability in this case. So there is a probability of 1/6 to pick this guy, right? Because you have 1/3, and then with probability 1/2, you pick this guy here. What is important now is to say, okay, that's okay. I have to, I have to consider this guy, but the value that he is going to add to this sum is going to be 0, right? So in this case, the value of this guy is 0. So for all the paths that don't generate a tuple, actually, you can say the value is 0, okay? And then to answer the previous question, actually, or to estimate this value, what you need to do is to do an estimation based on the path. So you can think about the following. You can think about the random variable that assigned to a path. I'm going to use this notation gamma here, this value of gamma, right? This value which was the T4, or the value of the tuple in the column D when you have a complete path, and when you have a partial or something that is top, I cannot go through all the relations, actually have value 0. So then actually you could use X as an estimator of the value that we're trying to compute, but this is a bias estimator, right? Because we don't consider that different paths can have different probability, and they can have quite different probabilities. So then the question is how to transform this X into an unbiased estimator. And the idea here is very simple. It's this idea of Horvitz-Thompson, which is just consider consider another random variable which has this value and just divide it by the probability of the path, actually. It's very simple, the idea. So if you do that, actually, first notice that what is going to be the expected value of this random variable, right, is going to be the sum of all the path of the probability of generating that path times the value of the random variable. And the probability of this guy is this, and the value of the random variable is B of gamma divided by the probability of this guy. Then you simplify these two quantities here, and you obtain exactly what you were expecting, right? You sum over all paths this value B of gamma, which for the tuples which are in the join, you are summing exactly the value in the last column, in column D, right? And for the other guys, you are adding 0, right? Is that clear? So this is the whole idea of Horvitz-Thompson, actually. So you would say, why someone, it's a very simple idea, but it works really well, actually. Okay, so let me try to formalize this and show you why this is a cool idea. So, well, this idea from 52, right, from a paper of Horvitz-Thompson, and I particularly recommend this book, which is by Thompson, not the same Thompson, which is a book just called Sampling. And it's a very nice book, actually. It has like everything that you need to know about sampling.
Is it 1912 or 2012?
No, 2012. No, 2012, yeah. A good point, actually. 2012, yeah. Okay, so the idea is very simple. Suppose that we have a list of values, B1 to Bn, and we need to estimate this value, the sums of these values, right? It could be the average, then you are going to realize that you can estimate many different things, right? So to do this estimation, what we do is we construct a sample of size n of little n, the elements from this set here, right? So we're going to say we're sampling the element position 3 on position 5, wherever, that has some value, right? We can do this with or without replacement. It's not a problem, actually. And suppose that now we have this x of I, which is the number of times the element I appears in the sample, right? If you are doing it with replacement, it could be several times. If you are doing without replacement, it could be 0 or 1, right? So then define this p sub I as the expected value of this variable x sub I. And then what you get immediately is that and this is what is called the Horvitz-Thompson estimator. This is an unbiased estimator for the sum of these values. And how do you construct this unbiased estimator? You just say, I have to multiply x sub I by the value b sub I that is associated to this element, and I have to divide it by the expected value of the random variable, right? Very simple. And actually, if you think about this is the same, because just for the I in the sample, this value could be different from 0, right? This is the same as saying I have to take all the values in the sample and I have to compute this quantity here. And here is where you have this inverse weighting that was mentioned, you mentioned this, right? No, good, yeah. That is very useful, actually, when you are doing these estimations. And notice that here it's very simple to see that this is unbiased, right? The expected value of y, which is going to be the expected value of this quantity. By linearity, we know that it's going to be the expected, these are just constant, right? So it's going to be the expected value of x sub I. And here, since we put the expected value here, it's going to be p sub I. You can simplify these things, and you are going to obtain then the sum from I equal to 1 to n of this b sub I, this is tau, right? So you get an estimator that is unbiased. It's a very, very simple idea, and it has been widely used. Let me show you just one example. So if you have You sample uniformly with replacement. So in this case, the probability is 1 divided by n, right? Then you can think of this variable x sub I as a sum of just variables, let's say, that have a second index k, where this variable could be is 1 if I is the kth element sample, right? So you're saying, okay, we're going to do n samples here, right? So, this is a very simple way to think about this. And what it tells you immediately that since these variables are distributed Bernoulli with probability p, these are going to be distributed binomial with parameters n and p. It's a very simple thing. So what I wanted to mention here is that this p sub I is going to be the expected value, right? The expected value of a binomial distribution np, and your Horvitz-Thompson estimator is going to be in this case this value here, right? You have to replace this p sub I by np, and since the probability is 1 divided by this big N, then this is going to be the estimator, right? So you're going to say we have to compute this big N divided by N, and then we have to do this sum here, okay? So probably, yeah.
Xi is 1, right?
No, it depends on whether it's with or without replacement, right? If it is without replacement, this will be 1, right? You just need to compute the sum of this b sub I. But if it is with replacement, then this could be larger than 1, right? So you have to consider these quantities. Yeah.
If it's with replacement, doesn't pi change as well?
No, in both cases you're going to obtain the same. Yeah. Yeah. I can show you that. I have some slide about that.
Okay.
Yeah. Okay, so it's a very simple idea, actually. Probably at this point you are thinking why this is used so often. And one of the reasons is the following. Consider the variance of this estimator, right? And to consider the variance, you are going to need the expected value of this x sub I times x sub j, right? And call this p sub ij. One thing is that this value is not necessarily equal to the multiplication of the expected value for x sub I times the expected value of x sub j. And the reason is that these random variables are not independent, right? You know that x1 plus 2 x sub n is equal to this little n, right? Because you are computing n samples, right? So we are not going to compute this explicitly, but what we are going to get is an expression that looks like the following. When you are computing this variance, actually, you are computing the expected value of I squared minus the expected value of I squared, right? And this looks like this. Then linearity, right? We replace this sum here, actually. And at the end, actually, linearity, you introduce this here, actually, and this is the expected value of x sub I times x sub j, and we have a notation for this is p sub I j, right? So you get an expression like this one. So this is an expression that you can compute if you know the exact distribution of the variables that you are using. But the cool thing is the following. In practice, something that you need to do is, if you are going to provide a confidence interval, in general, you need to have an estimation for the variance, right? So the question is, how do you do an estimation of this variance here? What would be the cool thing to do? What kind of estimator you would like to use to estimate the variance?
The same.
The same, exactly, yeah. Horvitz-Thompson again, actually. It's very simple, actually. The only difference is that now these are the values, actually, that you have to consider, right? You use Horvitz-Thompson again. So you say, okay, in this case, how do we estimate? We use the same thing again, actually. And this is a very cool feature, right? You say now my value, which is this b of ij, is this quantity that I have here, right? And once I have that, I know that the variance is going to be the sum over all ij of these quantities that I have here. This is what I showed before, right? This is the variance, right? The sum over all these values here that I'm calling b of ij. So what you're saying is, okay, I have this sum here. I know how to do this with Horvitz-Thompson. The only thing that I need to say is, okay, to get an estimation, I need to have this variable x sub ij that are defined as the multiplication of x sub I times x sub j. And here I have to put the expected value of x sub j, which is this p sub ij, right? That we have a notation for that because it's expected value of the multiplication of these two guys. And then, so if you replace, if you use the definition of a Horvitz-Thompson estimator, here you need to put the variable x of ij, and here you need to put the expected value of this variable, and here you have to put the value that you're trying to compute, right? And this is what you get. So you get, again, a Horvitz-Thompson estimator from the variance, actually. So you can use it again, right? And you get a very simple estimator. And you can do this over and over again, actually. So it's a simple idea that can be used and reused, actually, to do estimation. right?
Variance of the new variable root?
Okay, this is a really good question. The thing is that there is no like a general theory that tells you how it's going to be the variance, right? So what you have to do is you have to do it case by case, right? So it's not necessarily good. It's not necessarily a good estimator, actually. Yeah. Okay, so I have like half an hour. So one thing to keep in mind and to remember about this is like Horvitz-Thompson can be considered as a family of estimators, right? It's really an idea how to construct estimator that can be used actually in many different scenarios. So this is, I suppose, why it's like a nice idea. Okay, so let me show you one example of estimation on databases, and then I will move to the next topic. So let me show you this how do you do something like this, like a simple query. I mean, with this Horvitz-Thompson. So you have here the sum over V of this relation. You want to do this by using sampling. So the result of this query will be to do the sum of all tuples and taking the attribute B, right? So this is what you are doing here. And to do this estimator, actually, you can do different things. Actually, in simple random sampling with replacement, you are going to just select tuples and with some probability. So you do something like, well, in this case, with uniform probability, you generate uniform and random some tuple R in R. Then you add R to the sample, and then you say, well, this X of R is going to be the number of times the tuple R appears in the sample. Very simple, right? What we saw before, the expected value of this random variable is going to be n divided by the size of the relation, and then you get this Horvitz-Thompson estimator, right? Which is going to be this the size of the relation divided by n, and you have to consider, well, the samples, so you have to multiply the value of this X of R times the value that you have for this element. It's a very simple thing, actually. And then you can compute the variance. I'm not going to go through the details, but you get, okay, like I can show you this. You get like an expression like this one, actually, right? It's a variance that depends essentially on the size of the database. This is the variance of the values in the database. It's like saying, okay, I have some values and I can compute like the average, and I can measure how far are the elements of the database from that average, and it's divided by n. It's being reduced when you have more samples. Okay. So any questions?
So this one is actually for the column on which you compute the
Yeah, exactly, for the column. For the column, actually, you take the average, and then you measure how far are you from that average, actually. So it depends on that, which makes sense, right? Depends on how different are the values that you have in that column. Yeah. Okay, so if you want to remember something from this tutorial, I mean, this Horvitz-Thompson is really useful as an idea to construct estimators. And then, well, I'm not going to go through this whole thing. So all these were ideas where you were using once and again the Horvitz-Thompson different. I mean, you will have access to the slides, so it's fairly complete, actually. Okay, so what I want to say, there. Yeah. Okay. So what about other operators? And now let's move. And since I have like 20 minutes to the projection, actually. So the previous techniques can be easily extended to consider the selection operator. Actually, when you do selection, the only thing that is important is that if in the tuple you don't satisfy the selection, you have to put value 0 to that tuple, or depending on the application that you are doing, right? If you're doing the summation, actually put value 0. It's very simple, right? But the inclusion of projection is way more challenging. So let me just say a few words about this. So what is left is that we now consider joint selection and projection. So what we're considering is really conjunctive queries. And our goal is to show how to do efficient cardinality estimation for acyclic conjunctive queries. And efficiency here is put like this because we are thinking about polynomial time, actually, but really in practice, you want something much faster, right? I mean, you want something like linear time, yeah.
Under backward set semantics.
Sorry? Under set semantics. Under set semantics, yeah. Yeah, that's a good question, actually, about under back semantics, where this works extend, yeah. Okay, so one thing that is important to mention here, I'm going to represent this query, and I'm going to give you an intuition of how this thing, goes, and the estimation. So one thing is I'm going to use first order notation. So this is the query that we had before with the cardinalities. This is an acyclic query, right? And with the cardinalities that we were computing, right? And okay, so the query was something like this, right? If we write it in first order logic. But now suppose that you consider something like, okay, so I'm sorry, I'm also changing here the relations, but I'm using this notation. So now suppose that you quantify over some variables actually. And here you want to return just the x and w actually. X is this value that you have here, and w is the value that you have there actually. So then, if you compute the answer to the query, you're going to see that these are the tuples in the answer. And the problem that you have now actually is that if you want to count the number of answers actually, if you think about the information that they computed here, is not very useful, right? Because, I mean, you know that for this tuple, it appears 6 times, actually, but you know that this value 6 that you have is the value that you have here, actually. If you have this value here, you don't know how it's related with the value that you have there, actually. It's like, okay, what do you do here? If some of the variables that we use for the join, in particular, the value, in this case, is the value of the variable set, actually, is not part of the answer, right? So it's some value that somehow was quantified inside, actually. And remember that we know that for acyclic queries, the problem of counting the number of answers is sharply complete. We know it's a difficult problem. So this algorithm cannot work. So essentially, the problem here is that these variables, actually, the one that I put a star here, they're like anonymous, actually, when you're computing the answer. Once you have the answer to the query, once you know that you have value for 6, you don't know which values you use to compute this for 6, actually. And this is something, actually, and you don't care about this. I mean, the answer here is I mean, the number of tuples is 3, and I should say 3 independently of how many different ways I have to generate this tuple here, right? Okay, so how do you deal with this problem? And the main ingredient here is tree automata. So if you're going to learn something cool in this talk, it's also about tree automata. If you don't know about this, it's an extension of word automata, which is a really good representation of this acyclic conjunctive queries. So the idea here is the following. So I will show you how this works, but first, just a brief introduction to tree automata, just in case, I mean, you don't know how they work. Actually, these are automatas that work over trees, right? So they work exactly as a word automata, as a non-deterministic finite automata. You start by assigning some state to the root, right? And then you have some rule that tells you what are the states that you can assign to the children, right? And the rules look like this. You say, okay, if the state is P and I'm reading a symbol A, then, and here I'm considering like rank 3. So I'm saying, okay, I'm considering that I have 2 children, and I'm saying, okay, the states that I have to assign to these guys are Q and R, right? So you will say, okay, I have to assign state Q here, and then I have to consider the rules that I have for this element here. And here I'm saying, okay, this is a lift, so you expect to find a rule of this form that is saying, okay, if I have state Q and I'm reading a B, so I don't want to assign any state to children. This lambda is the empty string. So what I'm saying, okay, this could be a lift. It's okay. So this part of the computation is okay. And we can continue with the other part. We were assigning this state R, and we were trying, and now we have to continue here. Well, whatever is the rule that you have there, you have to continue assigning the states, right? Okay, so what is a tree automata then? I mean, if defined this way, what you're going to have is just a set of states, just as before. You are going to have some alphabets. It's a fixed alphabet, actually. Like I'm saying, I'm considering all the trees where the labels of the nodes could be A or B. You're going to have a set of initial states. This is very important because you assign this when you say, okay, I have to start from some state. They come from I. And we are going to have some transition relation where we have this rule that tells things like, when I'm in a node with state P and I see an A, I have to assign Q and R to the children, right? It's a very simple rule. Okay, so let me do one example. Everyone here knows tree automata? No. Okay, good. Yeah. Great.
States are uniquely labeled, so the alphabets can repeat, but
yeah, the trees is uniquely labeled. You are given a tree where you have for each node you have a label. Yeah.
This is the top-down automata.
Yeah, this is a top-down automata. You can also have bottom-up automata, right? Yeah, and they are equivalent. So this is top-down. Where I'm going to show you some example with this non-deterministic. So you can have for this combination you can have several of these triples, right? And you can think, I mean, it's not difficult to define it bottom up, and they're going to be equivalent, right? You can transform one into the other. So the non-deterministic top down is equivalent to non-deterministic bottom up and deterministic bottom up. Yes.
The acceptance condition is that you can complete.
Oh yeah, I'm going to say in a second what is acceptance condition. Yeah. Good that there are people here that don't know.
And deterministic top down is different.
Yeah. Yeah, okay, here we have the expert, yeah. Deterministic top down, and you're going to see in a second why it's different, yeah. It's less expressive than the other. Yeah.
transition relation, you have one rule for every state. Could it be if you are at P, if you see B, but that is not defined? Like for every state can have only one alphabet, or
Okay, so it's exactly like a non-deterministic finite automaton. For this combination here, I could have several of these rules that tells me how to move actually what state to assign. If it is empty, so for example, if you reach this thing here and you don't have a rule like this one, or you don't have any rules, it means that you fail, right? You cannot do anything, right? So this is one of the reasons to fail. And you can have several, and you have to pick one, like in a non-deterministic finite automaton, right? Yeah. Okay, so let me show you an example, one that I think is cool. So we would like to design a tree automaton that is going to check whether you have an even number of A's in the tree, right? This is what we want to check, right? Even number of A's. Okay, so we're going to have two states, E for even, O for odd. And you start from the starting state should be E, right? So we are trying to say in the whole tree, we're going to have an even number of states. And then we have to start assigning states to the children. And if you think about how we do this, actually, what you are saying here is, okay, in the whole tree, I want to have an even number of A's. Since I have an A here, what it should happen is that from here, I should have an odd number of A's, right? And this could happen if I have an odd number of 8 here and an even number of 8 here, or the other way around. I have an even number here and an odd number here. So how are the rules? The rules should say something like that. So one possible rule, it's if I'm in state A and I'm reading an A, for the children I should have EO. So I'm saying even odd. And the other rule, which is OE, right? And here you get an intuition why what Wim was saying, right? If this is deterministic, there is no way to do this, actually. You don't know how to guess what you're going to assign to the children, right? And we continue going like this. Right now we say, okay, assigned E, and in this case I say, well, if I want to see an even number of A's and I'm in a leaf which has label B, then this is okay, actually, because I'm seeing 0 A's. So I have a rule like this, right? This rule that tells you, in this case, with this leaf, everything is okay. You can stop the computation in that part. And we continue here, like now we said we need to have an odd number of A's. Since you are reading an A here, you should have an even number of A's here. And then it could be both even or both odd, right? And you continue like that. You say O, and you say, well, okay, I'm going to have an odd here. I'm reading I'm reading a B, so I need to have an odd number here. So it has to be even odd or odd even, and you keep going, right? And in this case, you are going to accept this tree, right? So the acceptance condition is that you have a running, an execution where you can finish without having this problem that you don't have a transition for some state, actually, for some combination, right? Of course, you could have guessed in the wrong way, like I could have said even, which is not the case here. And what is going to happen is that, okay, when you get here, actually, you're going to say even, but you are not going to have this rule, right? Rule that say if I have even and I am in a leaf, I'm going to allow that. So this is not going to be a rule in your tree automata, so you are going to fail here. And the acceptance condition is that you accept the tree if there is one execution that accepts the tree, the usual thing, right? Okay, so tree automata are okay, and I will show you in a second why it's a good way to represent acyclic conjunctive queries. Sorry.
Did you say that this is not complete? That if you had the other way of that, if you had odd number of A's here and even number of A's on this side, then it could not, then it could fail?
Yeah, what I'm saying is, what I was saying is that, okay, this was a successful execution, right, and running, which was successful. But what I was saying is that for this tree, you could have some runs that are not successful, right? So for example, if I was guessing EE here, right? But that's not the problem, right? I mean, in the sense that the acceptance condition at the end is that you accept the tree if there is an execution that is successful, right? Exactly like non-deterministic tree machines, right? Yeah. Okay, so something that is nice about this model is that what I was going to say is that you get the good properties that you have for automata, right? So you can decide containment, you can decide equivalence. I mean, there are many nice algorithmic properties, actually, in a model that is more general than word automata. And actually, it's a nice way to represent our problem because of the following. So think about, we have the previous query, We have the relations and the answer. And we are going to represent this by using a tree automata. So how do we do this? First, we have this idea that the values that were quantified, somehow they need to be anonymous, actually. We don't care about this value when we are counting. We care about this value when we are checking whether something is in the answer, right? So let's say that we use these symbols, this R4 star and R5 star. So we are saying, okay, we don't care about these guys here, right? And we do the same for all the values that should be considered as anonymous. For example, this W is something that is in the answer, but it's not in the answer here. So we're going to have all these stars here. Yeah.
So wouldn't you need to care about them if you join all them?
Exactly. We need to care about that. And the way that we are going to do this is by using the transition of the automata. I will show you that in a second. This is very important. Yeah, obviously. If you just keep this, I mean, there is no way that you can count, right? But the automata is going to take care of that. Yeah. So in the automata, this is going to be the alphabet, because we will be constructing trees where we have this symbol that somehow say, okay, this is a tree that tells you that this tuple should be in the answer. Okay? I will show you in a second how it works. And then the states are going to be the real tuples, actually, because we need somehow to say, okay, when we're constructing this, it's possible to join the elements that are in the, there is a way to generate this where I'm doing the right joins, right? Okay, so the states are going to be all the tuples that I have here, okay? So in a second, I will tell you how this works. So suppose that, for example, we have the answer for 6. So in that case, actually, a witness for this is this tree here, actually. This is a well-constructed tree where we say R46, and I'm doing the join with this in the value 4, also the join here with the value 4, and here I'm taking 1, I'm doing the join with 1 here. So this is a well-constructed tree. But this is not what we are going to consider. What we want is something like this. We would like to say, this is going to be the tree, because why I want to do this? Because I want to count for 6 only once, right? So the problem here is that if you think about for 6, there are different ways to generate this, right? And I don't want to count all of them. I just want to count only once this for 6, actually. So the way that I'm saying that is saying, okay, this is a structure that I want to say that represent this tuple for 6. This is the values that I'm using. And the states of the automaton are the one that are taking care that I'm doing the joins in the right way, yeah? And I will tell you in a second how, right? But remember that then for 4-6, we're going to have something like this. For 4-7, we're going to have a 7 there, only 1 tree that represents this guy, not several. And for 5-8, only 1 tree, right? We're going to have 5 here and 8 here, right? It's not like we're going to have several trees. We want to count this only once. Okay, so how this works is as follows. You say, okay, what should be the starting state should be the relation that we have here, because this is the root of the tree, right? So we're going to say, let's assume that we assign this state R of 4-6. And then the transition is going to take care of the joins. So the transition is going to say, if I am in state R of 4-6, and this is the symbol that I'm reading, so this is a valid one because I have the same value 4 here, right? So I'm not going to have a transition that says R of 4-5, R5 star, because this is not a valid way to think about how to produce a witness for this guy, right? So I'm just going to say, okay, in this case, if I have these 2 guys, right, then I will assign states to the children that somehow show you a witness for this that this tuple here is an answer to the query, right? So and I'm going to assign 5 of 4-1 and T of 4-3. Again, actually, I'm doing the right joins here because I have the value 4 here and the value 4 there, right? So I assign these states. When I assign this one, actually, in this case, there is a simple rule that says, well, if I am T43 and I have this, I'm reading this symbol here, this is something acceptable for a leaf, right? And in the other side, this is the important one. I assign this state, like S of 4-1. And what you do here is, okay, you have a rule, and here I have only 1 children, so you can have also rules of this form. If you have 3 children, you will have 3 states, right? So what I'm saying is, okay, if I have, I'm reading this symbol here, and in this state, I have to go to some state where I'm doing the right join, actually. And the right join here is this one here, right? Because here I have to join with the variable set. So there I'm taking care of that, right? And I'm saying, okay, this is one of the possibilities. I'm not going to have, for example, this U of 2, 5, 8 actually there. I'm not going to put that rule, right? Okay, so you do that, you assign this, and then you have a rule that says that this is consistent. So if you think about this, actually, what you are going to do at the end is that for every answer, you are going to have only 1 tree that represents the answer, and the states and the transition take care of this is a well-constructed tree, right? So what is the problem, actually, that we can reduce to is the problem of count the number of trees with 4 nodes that are accepted by the tree automaton, right? So produce that tree automaton, and now give me the number of trees of the tree with 4 nodes that are accepted by this tree automata. If you can count that, actually, you will be able to count the number of answers to the conjunctive query. Yeah.
Why these 4 nodes? Do we need this?
No. In this case, sorry, in this particular case, because you have 4 nodes here, actually, in the tree.
Yeah,
right?
yeah, but the problem is, I mean, you didn't construct so that it would only work for trees of this kind?
Just for, we're considering acyclic queries, right? So you have a joint tree. This joint tree is going to have k nodes, and
but your automaton doesn't enforce the skeleton of the tree. Your automaton doesn't enforce the skeleton of the tree.
In which sense, the skeleton of the tree?
Just how many nodes it will have.
No, it doesn't have that actually. But the way that it's constructed, it cannot generate, for example, in this case, a tree with 5 nodes, right?
Yeah,
because
so your automaton enforce.
Enforce that actually. Yeah.
So you don't need the restriction of 4 nodes.
No, but you need to. Yeah, actually, you are right. Actually, you could say, yeah, you're absolutely right. If you think about trees that are accepted, in this, good point. Actually, in this case, actually, you could say count the number of trees that are accepted by the automaton, because the automaton is constructing in a way that you can accept just trees of size 4. Yeah, you're right. Yeah. Okay, so I have very little time, so let me show you this connection. Then for tree automaton, there is this problem actually that is the problem of given a tree automaton or the alphabet 0, 1. This is not very important. It simplifies the problem. And a number of n, you want to count the number of trees such that t belongs to L sub t is accepted by the tree automata, and the number of nodes of t is n. Actually, this is the problem of counting. And this you could call it the sharp T8 problem. So this problem, okay, since I have like 3 minutes, and I'm missing the whole idea how you do this. This problem is related. I will do it here, otherwise I will have to skip like 1 million slides. This problem actually is related with a more basic problem, which is the same, but for non-deterministic finite automata, right? You are given a non-deterministic finite automata, and you're given a length n, and you are asking how many words of length n are accepted by the automata, right? This problem is a hard problem, it's Sharp complete. This problem also is a Sharp complete, obviously, because you can, the word automaton is a special case of tree automaton. And the type of reduction that you have between this problem and what are called parsimonious, which is a way it's a way for counting problem to represent many to one reduction. But in particular, it tells you that if you get a good approximation algorithm for one of them, you will have it for the other. So what we did in our work was first to think about how to construct a fully polynomial randomized approximation scheme, a good approximation scheme for this problem, actually. So there were only known quasi-polynomial approximation schemes. So there is a way, actually, that I wanted to show you how to do this. And the cool thing about this is that it uses the techniques that were presented in the previous part of the tutorial, right? So you have to construct an estimator, and for this estimator, and you have a confident interval that you can create from this estimator. And for this estimator, actually, you have to do sampling. There is a way to do it, and at the end, you have to use Hefting inequality to bound and to finally prove that what you are getting is a good approximation algorithm. And then we did the second step that was to go to this counting for tree automaton. It's a non-trivial extension. It's essentially the same schema that we are using there, but requires all the techniques. And from there, you can get the result that we wanted to obtain, which is this result that tells you that you have some polynomial time approximation scheme, a randomized, fully polynomial randomized approximation scheme for the problem of counting the number of answers to an acyclic query, right? And this tree automata, what I'm showing you, this construction also works for queries of bounded tree width or bounded hypertree width, actually, so you also get the results for those classes of queries. Okay, so let me jump to the last part of my tutorials, which are the open problems. Okay, I have like 1 million. Don't look here.
I am counting.
Yeah, I'm estimating. Okay, wait, yeah, okay. Yeah, sampling. Okay, so the final results. Actually, I can put okay. I was too ambitious, actually, right? But you keep asking and asking, actually, right? Okay, so these are the 2 results that was mentioned. Right? Finally, that the sharp T8 admits a fully polynomial randomized approximation scheme, and that from there it's possible to conclude that you also have the same results for the conjunctive queries, right? For acyclic conjunctive queries, this is very important. Okay, so let me tell you about research questions, and this, don't worry, will make sense given all that we saw in the tutorial. So I think that the first, like a big research question here is that development a general theory for estimation in query optimization. Really, there is no like something that and I'm citing this paper because this is an attempt to do this. There are some nice results there, but the questions are like this, like which estimator should be used given a budget, right? I have a budget to compute the query, right? And actually, even what is an appropriate notion of budget? But you define a budget and you are saying, okay, I would like to know what is a good estimator. What, I mean, how to do this in general, right? And in particular, what are optimal estimators if that notion could be defined? So these are, I think, interesting questions. It's important to understand for which relational algebra operators on aggregate it is possible to develop sampling techniques with good, strong, hopefully guarantees. Some of the techniques are used in practice. Actually, they show good results in practice, but sometimes you don't have guarantees, right? Or have weak guarantees, actually. So you would like to know that. And also, well, in particular, to develop very efficient algorithm to compute this estimator, right? This is an important thing. And also to understand the complexity of computing such estimators. And I'm talking about fine-grained complexity. I think it would be a lot of interesting work trying to produce like lower bound, concrete lower bounds for these estimators, right? The other thing is also understand for which relational algebra operators and aggregates it's not possible to develop sample techniques with the strong guarantees. I think this is also an important question, actually, to understand when you cannot do it. No, well, you could say, well, even for joint queries, right? I mean, like if you have joint queries and you are considering combined complexity, you really don't have actually, right? Because in that case, actually, you know from the hardness of the counting problem and the NP hardness of the decision problem, actually, that you cannot do efficient approximation, right? But again, actually, this is like the proof requires to have like long queries, actually. So we need to understand this better, actually, right? And even in the cases where it's not possible, actually, what kind of guarantees can be provided, actually? I think it's an important question, actually, to understand that. And actually something that, while I was listening to talks actually this week, something I think it could be very interesting is to try to understand whether these sample techniques can be used for some fundamental tasks for K-relation, right? When we have semi-rings, actually. I think there are could be lots of interesting, probably, I mean, they have been used, actually. It's just that I don't know about that. Or for example, for further logic with semi-ring semantics, that's something I learned this week, that the work from Gradle, actually. It could be very interesting to see what kind of things you can do with these techniques. And the last problem, and this is just something I like actually, but it's a very concrete problem, is like we have word automata, then we have tree automaton, then the next problem is like to count for context-free grammars, right? So we have a context-free grammar, we want to count the number of words accepted by a context-free grammar. This is a hard problem, but you want to know where there is an approximation, right? There is a quasi-polynomial time approximation algorithm by Cannon and other people, not clear at all whether this admits a fully polynomial randomized approximation scheme. Seems to be a very hard problem, actually. But I think it's a cool problem, so a very concrete one.
Okay, thanks, Marcelo. Questions? Oh, yes,
I want to come back to my question from all the way in the beginning. My intuition, which may be completely wrong, says that these kind of problems, for example, like for the first bullet, they actually become easy under back semantics. Is this?
Why?
Because much of the difficulty under set semantics comes from eliminating these duplicate results, right? And in back semantics, you can just keep
actually
going.
You are right. If you consider conjunctive queries under back semantics and you want to count the number of answers, it will be the same as counting without existential quantifiers. Actually, you're right.
It's just dynamic programming.
Yes, you're right. You're right. Yeah.
So this is definitely the theoretically interesting case, but maybe it also makes sense to at some point make something that gives you an overview of set and back semantics, such that this is also communicated to the world. If it's true.
No, I think it's true.
Paris.
So does the FPRAS algorithm say something about the data complexity?
The
the data complexity.
But which algorithm? Sorry, I didn't-
The FPRAS algorithm that you have, because this is more about combined complexity, right? So it says it's polynomial. Can it give you, in terms of data complexity, kind of a better exponent, let's say, or something like that?
We know that it's polynomial. It's not going to give you a better exponent, actually. Right? The algorithm has large exponents, actually. So yeah, if you fix the query, so some part of this is going to be fixed, it's not going to give you a better complexity. But I will have to think more about that. Yeah, that's a good point, actually. Like what we get from there. Right?
But it would be definitely better than the trivial algorithm that usually counts. It's going to be FPT.
Yeah, something like that. You are right, actually, something like that. But in terms of practical complexity, probably will not be faster, right? Yeah. Yeah.
Yeah, so the data complexity is polynomial time for every query.
Yeah. But it's just that whether this algorithm could provide something that is faster than the usual, like that, just the usual algorithm that you would use for a fixed query, right?
Right. But
Into the case.
my basic confusion is exactly the framework of your result. So the data complexity for any query is in polynomial time.
Yeah.
The data complexity, the combined complexity of any acyclic freeconnex query is in polynomial time. But if you remove freeconnex, then you prove that then it's no longer a polynomial time, and then you prove that you have an effective graph.
Yeah, exactly. Yeah.
So it's an acyclic query, but without the requirement of the freeconnex.
Yeah.
And it's combined complexity.
Yeah, it's for executive query. Yeah.
I'm happy to. More questions? Okay, that was a long week, so let's thank Marcelo. Enjoy the weekend, and I think